Welcome, my dear learners, for this course on mechanical vibrations. From today, we are beginning the module 2. In module 2, we will be discussing on forced vibration. So far, we have concluded our discussion on free vibration, that is both damped free vibration and undamped free vibration system analysis. Now, moving ahead for forced vibration system analysis, there are some systems in which the amplitude of vibration can be kept constant with the help of continuous excitation. For example, let us consider electric bells, which we have seen in temples nowadays. By continuous supply of electric power to the bell, we can maintain the amplitude of vibration. The sound of bell is generated due to vibration. This you people already know. I can maintain the sound of the bell constant by supplying electric power to it. Once I stop the electric power supply, the vibration will vanish, thereby we can't hear the sound of bell. Hence, by continuous external excitation, we can keep the amplitude of vibration constant. So, such vibrating systems in which the amplitude of vibration is kept constant with the help of external excitation are termed as forced vibration systems. Whereas in free vibration system, you people have already learnt that the vibration will decay depending on the amplitude of damping force present in the system. After certain amount of time, the vibration will vanishes because of damping in free vibration analysis. Whereas in case of forced vibration, the amplitude of vibration is kept constant with the help of external excitation, which is continuously acting on the vibrating system. Hope the concept is clear. Now the question arises whether the excitation what we are providing is harmonic or periodic in nature, or is it impulse, or it is random in nature. The external excitation what we provide might be periodic or impulse, or it might be random in nature. The very good example for impulse vibration analysis is transient systems. That is, large amount of force acting for a smaller duration of time is termed as impulse force. Such forces will cause transient vibrations. Whereas example for random vibration or random excitation is earthquake. Earthquake is a very good example for forced vibration because of random excitation. Now the question arises, is the excitation should be always external in nature, need not be internal, is the question arises now. The forced vibration might also because of internal excitation, which is nothing but unbalanced setup in the system. So in module 2 we will be discussing on forced vibration. That is, in this module 2 we will be addressing forced vibration. Now, as I said, for forced vibration there should be continuous excitation force. There should be continuous excitation force. Now the question arises, is this excitation force is always external? No, this excitation forces might also be an internal, which is nothing but unbalanced setup in the system. So the example for sources of internal excitation, the examples of sources of internal excitation are, the very first one is thermal effects. That is, in most of the mechanical systems which are subjected for heat transfer will be causing expansion, which is nothing but coefficient of thermal expansion of a material will cause expansion of material when we heat the engineering materials. So this will cause unbalance in the system, which might cause the vibration setup in the system. That is nothing but thermal effects. Next, second topic is resonance. What do you mean by resonance? Resonance is nothing but the frequency at which the excitation frequency is equal to the natural frequency of the system. At this point, the amplitude of vibration is very large. So due to which there might be an unbalanced setup in the system. This unbalance might cause vibration in the system. Next, moving for the another one, that is bearing defects. Bearing defects, which is nothing but there might be the connection between the parts of an mechanical engineering machines might be loosened. Because of this, there will be an vibration set up continuously because of the unbalanced setup in the system, because of loose connection between the parts of mechanical systems. That is termed as bearing defects. And next we have rotating unbalance. If we won't balance the rotating parts of a machinery, it will also cause vibration in the system, which is nothing but rotating unbalance, which we have already discussed in the course Dynamics of Machines, where we have learnt how to balance rotating parts of an machinery in order to avoid vibration. So like this, we have many sources of internal excitation also. So these are nothing but internal excitation which might cause forced vibration in the system. With this very brief introduction to forced vibration, let us derive expression for equation of motion for forced vibration with harmonic excitation. Keep that in mind, harmonic excitation. I will be discussing only forced vibration because of harmonic excitation in this module. I am not addressing impulse excitation or random excitation. I am addressing only harmonic excitation, periodic harmonic excitation in this module. Now let us derive expression for equation of motion for forced vibration with harmonic excitation, and also let us observe what is the system response. That is, today's topic is equation of motion for forced vibration with harmonic excitation. Harmonic excitation, with harmonic excitation. Sorry, here also I missed C, with harmonic excitation. Equation of motion. Equation of motion for forced vibration with harmonic excitation and system response. What do you mean by system response? System response is nothing but displacement as a function of time. Now let me consider the forced vibration system, which you people already know. A forced vibration system should consist of spring, mass, damper and continuous external excitation force. Correct? There is a continuous excitation force acting on it, F. I am considering this as periodic with harmonic excitation, hence it will be F naught sin omega t. It will be F naught sin omega t. Now at this point, let us consider there is a displacement because of applied force as x. Now what are the restoring forces acting? The restoring forces acting will be force due to friction, that is stiffness times the displacement kx, and force due to damping, that is cx dot, and also we have inertia force of this mass. Inertia force of this mass is what? mx double dot. And the force acting downward is what? The force acting downward is F, which is nothing but F naught sin omega t, where F naught is the amplitude of force. Now we know that for equilibrium, sum of forces must be equal to 0. Now if you see, these three forces are acting upward, whereas force F is acting downward. Hence I can write inertia force mx double dot plus damping force cx dot plus spring force kx must be equal to F naught sin omega t. So this is nothing but equation of motion for forced damped vibrating system, which is an second order ordinary differential equation. This you people already know. Now what is the solution for this second order ordinary differential equation? Now we should discuss the solution for this second order ordinary differential equation in detail. For damped free vibration system, there will not be any force, so RHS will be 0. For such systems, we have discussed what is the effect of damping ratio, that is when zeta is less than 1 underdamped system, when zeta is greater than 1 overdamped system, when zeta is equal to 1 critically damped system. We have studied what is the system response. Whereas now we have external excitation which is continuously acting in the system. Now in order to analyze this, the system response will be have two parts. One is transient part, another one is steady state part. Since we are assuming the excitation is periodic and harmonic in nature, the displacement should also be harmonic, but there will be a phase difference between the force as well as the displacement. What I mean to say is that if I consider the force which I have, that is T, I am applying force F and I am assuming it to be harmonic in nature, correct? So now if I consider the excitation caused because of this externally applied force, that is displacement x as a function of time, if I consider, let us take A as the amplitude of vibration, even this is also harmonic, there is a phase difference between these two, correct? There is a phase difference between these two. Let me take the amplitude of vibration as A as the amplitude of vibration, and here the amplitude of force is taken as F naught, correct? Now as I said, since we have the displacement also as harmonic, initially what happens, let me demarcate between the harmonic in order to understand nicely what is the transient, what I want to explain. So let us have the harmonic displacement like this. Initially what happens, the vibration will be transient in nature, it won't traces the harmonic part properly. After that it might follow nicely the harmonic path. So initial part wherein which we have the time for which the system is not tracing the harmonic path is termed as transient part. Transient. So this is transient part, and here we have steady state. Here we have steady state part. Now the solution, that is the system response in the transient part, is called as complementary solution, whereas in steady state part it is called as particular solution. So therefore the total system response, now if I consider the total system response, that is x comprises of complementary solution plus particular solution. The complementary solution is for transient part, whereas the particular solution is for steady state part. Now the complementary solution which vanishes after certain amount of time is already studied, that is the complementary part is nothing but f naught sin omega t is 0, that is mx double dot plus cx dot plus kx is equal to 0 is the second order ordinary differential equation for complementary solution, for which we have already know the complementary solution for underdamped systems is given by x of t is equal to c4 e to the power of minus zeta omega nt cos of omega nd t plus phi 2. This you people already know. What I mean to say is that the complementary part is already studied. The complementary solution, that is the complementary solution that is for transient part which vanishes after certain amount of time, which is nothing but undamped free vibration which vanishes after a certain amount of time is given by x of c is equal to c4 e to the power of minus zeta omega nt cos of omega dt, that is damped natural frequency, which is given by 1 minus zeta square into omega nt plus phi 2. Hope you people remember. Correct? So this is the complementary solution. Now what about particular solution? Now I should find the particular solution. Now find xp, which is continuous till the excitation is continuous. Now if I overlap this on this, magnitudinally f naught is not equal to a, correct? Leave about the units. This is displacement, this is force, I agree, but compare magnitudinally. F naught is not equal to a magnitudinally. If this is 15, this might be 20 or 30, like that. So what I mean to say is that there is a phase difference between these two. Since the externally applied force is periodic with harmonic force, the displacement is also harmonic in nature, but they are not exactly same. There is a phase difference between these two. Hence, the particular solution can be assumed in the form the amplitude A into sin omega t minus phi, where phi is the phase difference between the harmonic force applied and the displacement x. Now I should solve this and find what is the particular solution. The total system response, the total solution is the sum of complementary part plus particular part. This is what particular solution. Particular solution is for steady state part. Now let us find what is the particular solution. So this is the displacement, correct? Now what is the value of velocity x dot? What is the value of velocity x dot? X dot will be a cos omega t minus phi into omega, correct? Now I don't want this to be in cos, I want this to be in sin. So therefore what I will do, I can write this as, this can also be written as a omega sin of omega nt plus minus phi plus phi by 2. We know that sin of 90 plus theta is cos theta. Sin of 90 plus theta is cos theta. So I'll get the same thing. Correct? Now what is the value of velocity x double dot? X double dot will be differentiating this. If I differentiate this, what I will get? A omega square minus sin of omega t minus phi, correct? A omega square sin of omega t minus phi. So this can be written as what in sine form. So here I have negative sign, but I want sine function, but here I have negative sign. I want to remove this negative sign. So therefore what I can do for that, I can write it as a omega square sin of omega t minus phi plus pi, because sin of 180 plus theta is minus sin theta. Sin of 180 plus theta is minus sin theta. So I removed this negative sign by introducing pi. Hope you are following. I will tell you why I am using all this displacement, velocity and acceleration in form of sine function. Now what I will do, I will substitute these displacement, velocity and acceleration in our equation 1. Now substituting x comma x dot comma x double dot in equation 1 If I substitute in equation 1, what I am going to get? M x double dot is nothing but omega square A sine of omega t minus phi plus pi plus C times x dot is omega into A sine of omega t minus phi plus pi by 2 plus k. Displacement x for particular solution is what? A sine omega t minus phi minus, I will take this to left hand side, that will be f naught sine omega t is equal to 0. Now we can solve this equation in 3 different ways. One is using trigonometric solution, another one is using complex algebra, and third one is geometric analysis. The most easiest one is graphical method. So therefore I will go with graphical approach to solve this. That is the most easiest way to get the particular solution for this problem. So for which what I will do, I will represent this graphically. Hence I used the sine function in all displacement, velocity and acceleration. I expressed displacement, velocity and acceleration with positive sine functions in order to represent this graphically. If I use graphical method, I can get the particular solution more easily. Therefore let me go with graphical method. So in graphical method, if I represent, let us take the reference like this. Let us take the reference like this. Let us have the positive x-axis as a reference, and now the angle is omega t, right? We have the angle omega t. Let me take a line at an angle omega t first. Let me take a line at an angle omega t. Assume omega t as 60 degree or something and take it as a reference. I took omega t. So how much is this? This value is omega t. Now omega t minus phi, the force, spring force is acting Ka at omega t minus phi. So remove phi from this, where you have spring force. So spring force is acting at an angle omega t minus phi. Remove phi from it. Now two spring force at an angle of 90 degree, we have damping force C omega A. Now at an angle of 90 degree to this, we have spring force acting, which is C omega A. So this is spring force Ka, and at an angle of 90 degree to spring force we have damping force C omega A. Now the inertia force m omega square A is acting at an angle of 180 degree with reference to spring force. With reference to spring force, the inertia force is acting at an angle of 180 degree. So therefore at an angle of 180 degree I have the inertia force, that is m omega square A. So what is the angle between spring force and inertia force? It is 180 degree, correct? And at an angle of omega t we have force F is acting, but we have negative sign, very important, we have negative sign. So therefore at an angle of omega t we have force F is acting. So force F is acting in the opposite direction, correct? That is, the magnitude is F naught, is acting in the opposite direction. So therefore I should take it in opposite direction. Now we can see this angle should be omega t, right? This angle should be omega t. So this is the reason I used displacement, velocity and acceleration in sine form with positive values. Now what does this equation graphically mean? Summation of force is equal to 0 graphically means that it should form a closed force polygon. Now close this polygon. If you close this polygon, you will get the solution, correct? So this polygon should be a closed one. Now how to get the closed force polygon? That is, let us take equation 2. So equation 2 graphically means what? Equation 2 graphically means these forces should form closed force polygon. Closed force polygon, correct? So if I draw a closed force polygon, let me call this as O. Let me call this as O. Let me call this as O. Now how I will get the force polygon? At O, if I draw a line, so we have the force Ka, for which we have the force C omega A. Parallel to this, at an angle of 180, we have m omega square A, and the closing side is force F naught. This is force F naught. Now how much is this angle? This angle is known, that is omega t minus phi, whereas this angle is nothing but phi. This angle is nothing but how much? Phi. So this is the reference I took, O. Now I will drop a line perpendicular from here. I will drop a line perpendicular from here and call this as small a and small b. So graphically I represented equation 2. Equation 2 is nothing but this diagram. Now from this diagram I can find what is the displacement, amplitude, as well as the phase angle, phase difference phi easily. Now what is F naught square from triangle OAB? So from triangle OAB, from triangle OAB, I can write the force F naught square as, this overall length is Ka minus this distance is m omega square A whole square, hypotenuse square is equal to adjacent square plus opposite square, that is C omega A whole square, correct? Now I can take A common throughout. So if I take A common throughout, what I will get? If I take A common throughout, I can write it as A is equal to F naught divided by square root of K minus m omega square whole square plus C omega whole square under the root, correct? I taken A square common and send this to left hand side denominator and taking square root on both sides. So if I do that, if I take A square common throughout, and send this to left hand side denominator, it will become F naught square by the remaining part after taking A square common. Now you take square root on both sides, you will get this one, correct? Yes. Now the further simplification will yield us Now for better understanding, let me give the page number. This is page number 1. Page number 2 I have erased This is page number 3. Now moving for page number 4. Moving for page number 4. From here I want to simplify and find. So continuing from there, we have A is equal to F naught. Let me take K common. If I take K common, what I will get? Square root of 1 minus m omega by K whole square, m omega square by K whole square, plus C omega by K square. Now I can take F naught by K and write it as, I can take F naught by K and write it as static deflection, that is XS, because K is equal to F naught by X. So F naught by X is nothing but XS, static deflection, times square root of 1 minus K by M. What is K by M? Omega n square, right? So I can write it this as omega by omega n whole square plus C omega by K square. Now I want simplification, that is, the simplification will be, we know that omega n square is equal to K by M, that is what I have substituted here. Now I want substitute for C omega by K. C omega by K should be substituted, right? So what I will do, I'll multiply and divide by CC first, and also I'll multiply and divide by 2m. Omega n, correct? Now what you can write, recollect, what is C by CC? C by CC is damping ratio, zeta, CC by 2m. So CC is 2 root m omega n. So therefore CC by 2m can be written as what? Omega n into 2m by K. So K by m is omega n square, correct? So it is omega n square into omega n. Now if I simplify, what I will get? So here I have omega, C omega by K. So K is here, omega is here. Multiply and divide by CC, multiply and divide by 2m. So hence, what is the inference? So I can write C omega by K as 2 zeta omega by omega n. Hence the amplitude ratio, or it is also called as magnification factor. Magnification factor, A divided by F naught by K is written as XS, that is static deflection. XS is equal to 1 divided by square root of 1 minus omega by omega n whole square plus C omega by K can be written as 2 zeta omega by omega n whole square. So this is the expression for amplitude ratio or magnification factor, where XS, static deflection XS, is written as F naught by K, where F naught is the magnitude of force, K is the stiffness. Hope you followed. Now I can determine what is the value of maximum frequency, omega max, and also what is the maximum amplitude. What is the maximum amplitude and what is the maximum frequency? These two I can determine, correct? So to do that, what I should do? Now moving ahead for page number 5. Now moving ahead for page number 5, we have determined amplitude ratio or magnification factor, correct? But what is our aim? Our aim is to determine the total system response. Before that, let me determine what is the maximum amplitude and maximum frequency. Now for maximum amplitude, amplitude. When will you get the maximum amplitude? At resonance, correct? At resonance you will have maximum amplitude. Maximum amplitude will occur at resonance. What is the condition at resonance? Omega should be equal to omega n. The excitation frequency should be equal to natural frequency. So put that condition. Put omega is equal to omega n. This will become 1. 1 minus 1 is 0. This term is vanished. Omega by omega n is 1. So this will become 1. It is 2 zeta whole square. Square and square root will get cancelled. So therefore A by xs will become what? 1 by 2 zeta. So therefore maximum amplitude is nothing but static deflection divided by 2 zeta. So this is the expression for maximum amplitude of vibration. Now second one is maximum excitation frequency. To determine maximum frequency, what you should do? You should take derivative of amplitude ratio. Derivative of amplitude ratio with reference to frequency ratio and equate it to 0. Differentiate this equation with reference to frequency ratio omega by omega n and equate it to 0. If you do that, you will get the expression for omega by omega n, which is nothing but omega max by omega n as root of 1 minus 2 zeta square. Root of 1 minus 2 zeta square. So therefore maximum excitation frequency is nothing but root of 1 minus 2 zeta square into omega n. Root of 1 minus 2 zeta square into omega n is the expression for omega max. Hence we have calculated the system response. Hence the system response. Our aim is achieved. The total system response is nothing but complementary solution plus particular solution. So therefore complementary solution is C4, a constant e to the power of minus zeta omega nt cosine of root of 1 minus zeta square into omega n omega nt plus phi 2 omega nt plus phi 2 plus what is particular solution? Particular solution is a sin omega t plus phi, correct? xp I have written in page number 2. xp is nothing but a sin omega t minus phi. A sin omega t minus phi. What is the value of a? What is the value of a? A is xs by this term. A sin omega t minus phi. What is the value of a? Amplitude. Amplitude is xs divided by this one, correct? That is xs divided by root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square under the root. This is the value of a sin omega t minus phi, correct? So particular solution is a sin omega t minus phi. So complementary solution plus particular solution. Particular solution is a sin omega t minus phi. What is a? A is here. So this is continued. Don't get confused. This is continued here. So this is the expression for total system response. Now what is the value of phi? Phi is unsolved, right? That is phase angle phi. Phase angle phi is unsolved from triangle OAB, from force triangle OAB, from force triangle OAB. What you can write? Tan phi. Tan phi is equal to what? Opposite side by adjacent side. Opposite side is C omega A, adjacent side is Ka minus M omega square A. Throughout I can cancel off A and I can write this as what? Tan phi is equal to C omega by K divided by 1 minus M omega square by K. M omega square by K, correct? K I have cancelled, sorry, throughout I took A common in the denominator, A and A will get cancelled, and then I took K common and send it to numerator. This will become 1 minus M omega square by K, numerator is C omega by K. What is C omega by K? C omega by K is 2 zeta omega by omega n. M omega square by K can be written as what? M omega square by K can be written as omega by omega n, correct? So therefore, what is the expression for tan phi? Tan phi will become C omega by K, that is 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. Omega by omega n whole square. So this is the complete solution for the system response for an forced vibration with harmonic excitation. With this, I conclude this introductory lecture on forced vibration. That's all from this lecture. Thank you all.